All right, so I'm going to look at problem 2 here, and this is something I haven't gone over in class very well, but it's the idea that there's actually three different versions of plane equation. And so far, we've really focused on the Cartesian equation, which is just the one that's ax plus by plus cz equals d. But really, there's some other ways to write that. So first, let's start by finding our vectors, because we have 3 points. 3 points defines a plane. So vector AB is going to go down 1, up 1, down 3. Vector BC, or I guess I could do AC, it doesn't really matter. As long as you're utilizing all three coordinates, you'll get the same plane. So what does BC do? Goes up by 4, goes down by 4, goes up by 4. And so one word that they use a lot in thinking about linear algebra is to span. And so basically what you're taking is AB and BC, and you're adding as many scale multiples as you want. And so if you think about like a piece of paper that you could think of it like 8.5 by 11, you're just adding as many horizontal and vertical components as you want. They're not necessarily perpendicular, but you can still span the entire vector by adding scalar multiples of each of your two vectors. And that's the whole idea behind the vector equation of a plane, is the idea that every vector in the plane can be written as any point that's in the plane. Let's just use point A, 0, 1, 3, plus then a certain scalar multiple. For some reason, they like to use fancy Greek letters, but you could just use the letter T and Q or whatever letters you want. But they, in the textbook at least, like to use lambda times one of your spanning vectors, negative 1, 1, negative 3, and then mu times one of your other spanning vectors, 4, negative 4, and 4. And you can imagine that if you just made lambda equals 0, for example, then all you're doing is starting at a point in the plane and moving in one direction. If you made mu 0, you'd just be moving in the direction of the other vector. And if you did linear combination, so like 2 lambda plus mu, you can collect all of the possible points that are in the plane. So that's called the vector equation of the plane. I'm saying that all vectors are of this form. The parametric equations are really not too exciting. It's just taking each of those components and writing them in terms of x, y, and z. So x is 0 minus lambda plus 4 mu. Y is 1 plus lambda minus 4 mu. And z is 3 minus 3 lambda plus 4 mu. Just breaking it apart into three pieces. Then the last one, the one that I typically have focused on in class, the Cartesian equation, that one you just find by doing the cross product and then plugging in any of your given points right there. So let's try to knock that out real quick. So we'll do our determinant, ijk, negative 1, 1, negative 3, 4, negative 4, and 4. So we get I times 4 minus 4 minus j times negative 4 plus 12 plus k times 4 minus 4. That's weird, but I don't think I made a mistake there. So that gives me 0, negative 8, and 0. And so then we dot product our normal vector with any of the points in the plane, and I'll just use the point A, 0, 1, 3, like I did before. And so that would then be 0 times x minus 0 minus 8 times y minus 1 plus 0 times z minus 3, and that equals 0. And so that ends up just being negative 8y plus 8 equals 0, or in other words, y equals 1. So that is a very odd situation. I must have made some sort of mistake back there in finding my cross product, because I don't believe that all of our points have a y value of 1. Okay, So I can't find the mistake right now, but I'm sure that I made just some simple arithmetic error over here, or possibly I made an arithmetic error at the very beginning when I wrote down my original vectors. So if you find it, let me know and I'll fix the video. Thanks.